Hi, this video is about mechanical energy in physics. In some previous videos, I've talked about the concept of work in physics. Work is when you apply a force to an object and that object moves a certain distance. And I've tried to show how work is important because sometimes when you do work on an object, you give that object energy. And energy is the ability to do more work. So the way that this works out is that when a net force acts on an object and the object moves in the same direction, that object gains energy. So I've got a few examples to try to illustrate this. An archer pulls on a bowstring, stretching the string back, giving the bowstring elastic potential energy. Another example, a car engine drives the wheels of a car, propelling the car forward, giving it kinetic energy. The car moves and so it has kinetic energy. Another example, a father pulls his daughter back on a swing, ready to release her, pulls her back to a higher position, which gives the girl more gravitational potential energy. And then finally, gravity pulls the daughter down on the swing to a lower position, giving her kinetic energy. So in each of these situations, work is done, force and distance, and as a result of the work being done, energy is gained. But what I want you to notice is that the type of energy that's gained in these situations is either potential energy or kinetic energy. There's different kinds of potential energy, but it's either kinetic or potential. And that matters because kinetic energy and potential energy are often grouped together in physics using the label of total mechanical energy. So mechanical energy is this idea of kinetic and potential grouped together. So let's look at a classic example of this. It's classic for me because when I was in school, I would often get bored and I would take apart one of my pens like this. I would just, disassemble it, on my desk. And if I was really bored, I would start to just flick the pen up like this. Oops. I would make the little spring inside, shoot the pen across the room. If I was bold, I would go across the room. Usually I would just bounce it, right in front of me and catch it again. I would either do that or I would just flip the pen in my fingers and try to catch it. But I wanted to focus on this little situation here of just simply pushing down on a pen and letting it go up like that. Because it actually involves different forms of potential and kinetic energy. And it's a really good illustration of mechanical energy. So I've drawn this simple act of pushing down the pen and releasing it. And I've tried to show, we're going to try to label and measure the energy that's involved in each situation. So at first, when you push the pen down into the spring, there's a little spring in there that gets compressed. So I tried to illustrate that here. When you do that, you're doing work on the pen, pushing the spring down, and you're storing elastic potential energy. Now I'm going to make up a number here just to help illustrate how this works. I'm going to say that we store 10 joules of elastic potential energy by compressing the spring. I'm also going to say that the pen is starting out at a level of 0 height. So it doesn't have any gravitational potential energy or kinetic energy at the beginning when I'm just holding it here ready to launch. I'm not moving it, I'm just holding it there. So we have 10 joules of potential elastic, 0 of gravitational, 0 of kinetic energy. So the total mechanical energy means kinetic and potential together, grouped together. So to find the total mechanical energy, you simply just add up all the potential and kinetic energies here. And so the total mechanical energy is 10 joules. 10 plus 0 is 10. Now, when I let go of the pen, it starts to shoot up. The spring kind of decompresses or it expands. And so as it expands, it does work on the pen, pushing the pen up. And if we assume there's no friction or air resistance here, which I think is a pretty good assumption for this simple case, then all of that pent up energy there that was elastic potential energy, it turns into a different kind of energy. It turns into kinetic energy, this speed. So we're going to say that all of that elastic potential energy is gone. And what did it become? We're going to say that it became all kinetic energy here. And we're going to ignore the fact that, yeah, the pin does go up a little bit and gain a little bit of gravitational potential energy. We're just going to, for simplicity, say that it's still like at a zero height level. It hasn't gone up enough significantly yet to gain any potential energy, gravitational potential energy, that is. So what you should notice then is, based on this simple situation, all of the mechanical energy has stayed the same. If we add up 0 plus 0 plus 10, we still have 10 joules of total mechanical energy. Now, it gets interesting that as the pin continues to rise, it's going to go higher and higher, so it's going to be gaining gravitational potential energy, but it's also going to be getting slower and slower because gravity is acting downward on it and decelerating it. So it's going to be losing kinetic energy and gaining potential energy, gravitational potential energy. And I'm going to make up a number again here, but I'm going to make sure that it still adds up to 10. So I'm going to say that now, let's say it has 6 joules of kinetic energy, which would mean it has 4 joules of potential energy, gravitational, and 0 of elastic potential energy still. I made it this way so that when you add it up, it's still going to have a total mechanical energy of 10 joules. And we're saying that because it hasn't lost any of this mechanical energy. It hasn't lost any of the kinetic energy. The only kinetic energy that it loses, it gained in gravitational potential energy. So if we played this forward a little bit more, as the pin continues to go up, it reaches a max height, right? The peak of its trajectory. And at that point, it stops moving just for an instant. Like once it reaches the top, it's at rest. So at that point, the kinetic energy is 0. The elastic potential energy is still 0. And now we can say the gravitational potential energy is 10 joules. We're not losing any energy here, so the total is still 10 joules throughout. So throughout this whole scenario, the energy that we started with here has not gone away, but it has changed forms, or transformed, you could say. So the total mechanical energy is conserved. It's not lost or gained, but it does change individual forms. So this gets at the whole point of mechanical energy in physics. Why do we group kinetic and potential energy together? It's because sometimes it remains constant. So almost missed the hook there. The total mechanical energy is defined as the kinetic energy plus the potential energy, or energies. Written as an equation, you can write it like this: TME is total mechanical energy. So in some situations, the total mechanical energy of an object remains constant, even if the object is speeding up or slowing down. In other words, mechanical energy is sometimes conserved. And conserved is just the word we use to talk about the total is not lost, or we don't lose any of it, or we don't gain any of it. It stays constant. So you'll notice I said it's in some situations that this happens. Mechanical energy is conserved as long as non-conservative forces do not act on the object, which that might seem kind of obvious, but you'll have to see a future video to understand what that means. For now, we're just talking about certain situations where mechanical energy is conserved. So one other situation where mechanical energy is conserved is in a pendulum swinging. So if you take an object and you let it swing back and forth, for example, my microphone. If I let my microphone swing back and forth like this, you'll notice it continues swinging for quite a while. And it continues swinging for quite a while because if you can ignore friction and air resistance again, mechanical energy is conserved for a swinging pendulum. And I've drawn some bar graphs to show this. At the very beginning of a pendulum swinging, you raise it up to a tall height and you let it go. It starts out not moving at all because you're releasing it, but it has all potential energy at the beginning. If you add up potential, and kinetic, you get the total mechanical energy, which is a full bar in this picture. As it starts to descend, it loses some of that potential energy. So we've lost a little bit of potential. Whatever loss we had in potential energy, that is our gain in kinetic energy. And we know that's true because the total mechanical energy is conserved in this situation. So whatever loss we have in potential, it's a gain in kinetic, so that the total remains the same. As it swings all the way down to the bottom, the potential energy has all gone and turned into kinetic energy. So we've lost all of our potential. It's become all kinetic. Still, the total mechanical energy is conserved. As it starts to swing back up a little bit, it's going to get a little slower because it's gaining height, gaining potential energy. If you add up the two columns, it's still a total mechanical energy that stays the same. So this is hopefully a helpful illustration for how mechanical energy stays the same. Now again, this only happens in some situations. You'll have to watch a future video to see what exactly we mean by non-conservative forces. So that's all I've got for you in this video. Remember, habit is the battleground of character.